All right, guys, welcome to the first lesson for Unit 11 here on area. And we're going to be introducing quite a few formulas. So starting out here with triangle. So if we want to find the area of a triangle, our formula, if you recognize this, is just going to be 1/2 times base times height. So just to kind of unpack that really quickly, B stands for base, H stands for height, and that's how we would, we'll say those are the parameters that we would need to find the area of a triangle. For a parallelogram, our area is a little bit different. It's actually just going to be base times height. So we're no longer taking 1/2 base times height, but just rather straight away base times height. And notice how those are labeled in the diagram here, where the base is just along the bottom there. Height is if you were to construct an altitude within the parallelogram. Rectangle, you might recognize this formula to also be just area equals base times height as well. And again, this is getting kind of redundant, but base and height would be the parameters that we use for rectangle. Okay, next looking at a square, keeping in mind that a square is essentially just a modified rectangle. It's a type of rectangle where all of its sides are going to be the same measure. So with a rectangle being area is base times height, it's kind of a modified form because we're multiplying side by side, also known as just sides squared for a square. So all you need is just one parameter in this case, and that is the measure of one of those sides of a square to find its area. Next one we're looking at here is the trapezoid. Area for a trapezoid is going to be 1/2 of the height. So if I write this out, 1/2 of the height times the sum of the bases. So now we have to incorporate both of the bases for a trapezoid. And they'll be summed together and then multiplied by the product there out front. So this is, again, height, base 1, and base 2. Okay. A kite is different still. So there's this parameter in a kite called the diagonal. So if I were to connect the two kind of creases or corners of along the smaller direction, and then the longer two corners, those are my two diagonals, and those measures are indicated as D1 and D2. So for a kite, my area formula is going to use both of these values. And so if I write this out here, we are going to have that the area equals 1/2 of diagonal 1 times diagonal 2. Right, so we're taking a product of essentially both of those diagonals and then dividing it in half. So diagonal number 1, this guy being diagonal number 2. Okay, rhombus is very similar to a kite. As a matter of fact, it's going to have the exact same formula, 1/2 of diagonal 1 times diagonal 2, where again, diagonal 1 is going to be the length of one of the diagonals, and diagonal 2 would be the length of the other one. So it's essentially a modified kite. Circle, we're familiar with this guy. This is just pi r squared, right? That's nothing new here. We just need to remember that r represents the radius, not the diameter. That's half of a diameter. And then a sector is essentially a portion of a circle. So we'll say it's a portion of a circle. So we'll actually just be kind of scaling it. So we're going to take the full area formula, pi r squared, but then take whatever the angle is, the central angle that we're working with here, out of 360 degrees. So that's how that would look a little bit different. Okay, so now we're just going to jump into applying these formulas. Okay, first guy here that we're looking at, this is a rectangle. If we just look up to the top, My formula for a rectangle is length times width, where I have length, width. So if I input my numbers, I have 15 times 5. Remember whenever we are doing an area calculation, we want to make sure that our final answer is in units squared. So I'm going to have 75 feet squared. Cool. Next one, now we're working with a square. So if I look up at my reference and I know that area of a square is just side squared. So I'm just taking 3 squared, which is 9. And then we always answer in terms of units squared. So 9 inches squared. Area of a triangle, again, if I fetch my formula up from the top here, 1/2 of base times height. So looking at my values here, this would be my base, and this would be the height of my triangle. So I'm inputting my values 1/2 times 10 times 4. So that's going to give me 20. I don't have any units labeled here, so I can just abbreviate that as units squared. I'm outside, guys. Sorry if there's traffic noise. Okay, now we're looking at a trapezoid. This one's a little bit trickier because they're not giving us all of the particulars. So if I'm dealing with a trapezoid, formula for a trapezoid is 1/2 of the height, and then we're taking the sum of the two bases. Right? Because if we go back up here, 1/2 of the height, and we're adding the two bases. So base 1 up top here is just 10 inches. Base 2 is going to be the sum of both of these guys. And then this, here's where this is tricky. This 5 is pertaining to the hypotenuse of what would be a little right triangle here that I construct. But I want the height right here, right? So I'm going to have to do a little quick run through of Pythagorean theorem, knowing that we have a leg 3, an unknown leg b, and a hypotenuse of 5. And so if I rearrange here, b squared would be 25 minus 9, which is 16. Square root of b is 4. So my height is actually 4. So plugging my values in, I have 1/2 times 4. And then we're multiplying 10 plus 18. If I crunch my numbers there, I'm looking at 28 times 4, dividing that by 2 to get 56. So my area here is going to be 56 inches squared. Okay. Next one. Here we're looking at a parallelogram, which we know the formula is the same as a square, actually, base times height. They're giving us some extraneous information here. We don't need this 9. Really what we need is the height and the base, the 15 and the 8 there. If you just think of it as like a tilted rectangle in a sense. So I'm taking 15 times 8. It's just straight away my base times my height. And that should get me 120. And then we're dealing with units squared, so centimeters squared. Cool. Okay, next one we're dealing with a kite. We know from our formula up above, a kite is 1/2. If we just go back up here. Kite, 1/2. And then you're multiplying the two diameters. So we're taking 1/2 times, all right, we don't have the diameters fully labeled here. So this is where we have to kind of get creative. We see that these markings are telling us these are all the same. So that makes this a 2 and this a 2. So actually diagonal 1 is the full length of this guy right here, which would be 2 and 10. So that's a complete distance of 12. And then my diameter 2 in the other direction here is just 2 and 2, which is 4. So if I set up my 1/2 d1 times d2, this is actually 1/2 of 12 times 4. 12 and 4 is 48. If you cut that in half, that is 24. And then we don't have a unit again, so we'll just say units squared. Okay. All right, next one. We're now again looking at a trapezoid. Trapezoid. So this is again a trapezoid. Right, we know our formula from up above here. 1/2 height, and then the sum of the two bases. So my area is 1/2 of the height times the sum of the individual bases. In my diagram here, they're giving me a base 1 of 11. And then if I know this also has to be 11 right here from this distance. So altogether, this would be a 12 for my base 2. So really what I'm just missing is my height, which again, I can inspect that I have a little mini right triangle here with a base of 1 and a hypotenuse of root 50. So if I take this as 1 squared plus what would be the height squared equals root 50 squared, then we have 1 plus h squared equals 50. Subtract 1 from both sides, h squared equals 49, and square rooting, we get h equals 7. So my height here is 7. So now I have all of the particulars I need for my calculation, so I'm just taking 1/2 of 7 times b1, which is 11, plus b2, which is 12. All right, so if I multiply these out, I'm taking 13 times 7 divided by 2, so 45.5 for my measurement here, and this is in centimeters squared. Cool. Next one, number 8 here, is another triangle. And we know area of a triangle is 1/2 base times height, where my base is not completely known yet. I know that I have an 8 just from here to here. And look at this. They're being kind of cruel here. We have a 30, 60, 90 triangle. We could use trigonometric ratios to solve for our missing sides. Or if we think about our 30, 60, 90 ratios, let's write these up here. This is like a good review problem. 30, 60, 90 ratios being 1 to root 3 to 2. I said 3, but I wrote 2. That's silly. Root 3 to 2. Right, so right now if I have my hypotenuse, remember how how we were teaching this is like my 2a. So that, if 2a is 10, that's how do I want to fit this in? 2a equals 10. So that implies that a equals 5. I know that my 30-degree side is going to be just a, so this would be 5 right here. And my height is a root 3, which would be 5 root 3. So now I have my base and my height. Total base is 8, 9, 10, 11, 12, 13. Let's highlight these. So my base is 13, height is 5 root 3. And so now I can plug these values into my formula. So 1/2 of 13 times 5 root 3. Okay. If we want to be precise with our answer, I actually have 65 root 3 over 2. But with area, we typically like to have like functional answers. So if I change that to a decimal, 65 root 3 divided by 2 is 56.29 about. So it's about equal to 56.29 millimeters squared. That one is pretty complex there. Okay, now we're dealing with a rectangle, which we know just is base times height. But look at, this is a devilish problem again. We could classify this as base or height, but we don't know our height, right? So again, we're going to have to use right triangle relationships, which is the fact that this is a right triangle, terribly highlighted. Let's try that again. This is a right triangle. We have an angle here of 28 degrees, and I'm looking for this measure here that's starred, because that's going to be the same measure across the way here. So noticing that with respect to angle 28, or the 28 degree angle here, I have an opposite sign and an adjacent sign. Do you guys remember this is going to use the tangent function? So I could build this and say tangent of 28 equals 7 over the height, which I don't know. And so to isolate my variable, I'd need to take 7 divided by tangent of 28 to get my height. This is definitely going to be a decimal approximation. So if I take 7 divided by tangent of 28, we get 13.1 7. So height is about equal to 13.17. So that's what I would use in my calculation, along with my base of 7. So my area then is going to be 7 times 13.17. So if I multiply these together, we get 92.19. And we do want to do this in the proper unit, so inches squared. Okay. All right. Next, we're looking at a square, and they just can't give us any leeway here, right? Because area of a square should be simple enough. It's just side squared. But they're not giving us the side, unfortunately. They're giving us the hypotenuse of what would be a right triangle if I constructed it inside this square. Right? 3 root 2 is like the hypotenuse. Notice this is a 45, 45, 90 triangle, and we have special patterns there. Let's write it up here. So 45, 45, 90. Remember, the sides exist in a ratio of 1 to 1 to root 2. So if I have the root 2 side, this is like my a root 2 right here, then that makes my a value 3, which makes both of my sides 3 because those are existing in a ratio of 1. So my side is 3, meaning area is just 3 squared, which is 9, and we're dealing with centimeters, so centimeters squared. Now we're looking area of a sector. So we said area of a sector, it's essentially just the triangle formula, pi r squared, but then you're going to multiply it by the measure of the central angle out of 360. So in this case, my central angle is 90 degrees, as evidenced by that little box. So I'm taking pi times my radius of 14 squared times 90 out of 360. So if I go ahead and do 14 squared times pi times 90 out of 360, we should get 153.94. So we'll say area is about equal to 153.94, and we'll go with millimeters squared. Cool. And then last one, the sector is a little bit larger. It's still the same formula, pi r squared times the central angle out of 360 degrees. But now we're just looking at the fact that this is my theta, my central angle there. If I see that I already have 120 degrees used up out of my 360 degree budget, that leaves me with 240 degrees remaining in my rotation. So 240 degrees would be my theta. Radius is 7. So my area is going to be pi times 7 squared times 240 out of 360. And then now I'm just crunching the numbers. So 7 squared is 49 times pi times 240 out of 360. And then we should get 102.63 if we were to approximate. So area is about equal to 102.63, and then we'll go with centimeters squared. Cool. So some of those are pretty tricky applied area formulas, but that's it. Thanks for watching, guys.